In this segment, we'll look at a commonly occurring situation where we're superimposing two beams of light, or two waves. Really, it's holes in general for two wave sources. So we'll think of it as a two-beam interference, and think of these as light beams. Again, this is a very common situation that you have in which you're really adding and superimposing two waves and looking at it, what you perceive at a given detector. And very often in optical work, you have two sources, and you want to recombine those to get interference with some detector. I'm going to assume that source 1 is a distance x1 from the detector. The detector could be your eye. Nowadays, it's probably some sort of photo detector of some sort, and S2 is a distance x2 from it. But to make life simple, usually both of these beams generally arise maybe even from the same source, but so they have exactly the same frequency, same omega, and the same wave number k. And like I say, very often this is arranged by having them go through different paths in a circuit and then recombine them again over here. So a pretty common experimental situation. But in general, could be used for any wave. These could be sound waves. Yeah? The interpretation is a little bit different, and it could be water waves, and you're looking at the height of the wave over here. So it's a general, very general wave phenomena, with the exception that they both have the same frequencies. So we're looking at a very specific case. The total wave that hits the detector at time t is just the superposition of these two waves that come from various sources. And we know, if I use the cosine, I know a wave is, in general, cosine kx minus omega t plus the phase. I'll keep the phase separate from the amplitude, so this is a real amplitude. All of this is a real quantity here. But since my detector is at this point at x1, this travel from this source a distance x1. So we've seen that. I'm also assuming that this x1 is large enough so that we're by the time it reaches the detector, I can use the plane wave approximation. And so the superposition of these two waves, the only thing that's different about them is that one travels a different distance than the other one. They may also have different phases here, phi1 and phi2. But all of these are real quantities up here. Now it's going to be easier, and it is in general, whenever you have cosines or sines, I could have used sines here, to go to the complex form. And so I could represent this first wave in its complex notation, and the second wave in its complex notation. But I'm going to be adding those two, superimposing them to get the total, in our case, electric field at the detector at time t. Okay? And the thing to note on this is the way we've set this up. E1 and E2 are still both positive amplitudes. And we want the intensity that's observed. In general, detectors detect the irradiance, really the time average value of the intensity, and that's related to for electric fields in this fashion here, as we've seen earlier. In general, this E is a complex entity, and so I have to take the complex modulus squared, which is the same thing as E star E, and that's what I did below. This quantity for the intensity at the detector is this. The electric field E is this expression. In here I have to take the complex conjugate times the field back to itself, and that's what we mean by this symbol here. And then it's really just a matter of some algebra. Complex conjugate, just to recall, is everything in here I switch I to minus I. And so this term becomes this, just the i's go to minus I, and this one stayed the same. And now I need to multiply this out, and it's just expanding these with these two factors. So it'll be the first term times the first term here, and you'll notice that they have exactly the same argument for their exponentials except for a minus. And so this is the inverse of that, and I just get E1 squared. First term times the second term, I'll get a cross term here, which is this term, and this term here, and then E1, E2. And then I take the second term times the first term, so I get another cross term, but now I get the minus on the first one, and multiply this times this, and here. And then finally, the second term times the second term. Again, that just gives me E2 squared, and this is the E2 with a minus I, and then E2 over here with the with the plus I, E2. E2 times here times this one, so that the minus of these two terms are identical, and so we just get E2 squared. Again, E1 and E2 are all real numbers, and so this is just the square of real numbers, square of real number. I reorder it, so I'll multiply through by this 1/2 epsilon c, and I notice these two terms have a common factor, so I can pull it out, put this term second, and then the cross terms, again, they've got a common factor, so I pull it out. So I get a 1/2 epsilon naught c times E1, E2, and then I can combine these two exponentials into a single one. And when I do that, the omega t's go out. The terms that are left, I'll get an k2 x2 plus v2 minus k1 x1 v1. The t's, and then the second term here, likewise, when I look at that, the omega t's go out when I combine these two into a single exponent. And then if you look at those, I can take this half and put them underneath here, and you find that these two terms, that's what's left, are just k2 x2, k2 x2, phi2, minus k1, kx1, phi1. So both this part and this part are identical, and the exponents, except for the overall minus sign. And so the sum of these two is just divided by 1/2 is just the cosine of the common phase that they have. Sure. So now everything is back to a real number. We identify that this is just the intensity of the first beam alone. This one is just the intensity of the second beam. And then I've got this cross term here, which if you look at it is really usually called the phase difference. I'll indicate it with a delta, and that's just alpha 2 minus alpha 1, where those were the original phases of the waves. And if you do these calculations, alpha 2 is kx2 plus phi2, and alpha 1 is kx1 plus phi1. And I think if you look at those, that's the same as up here. Okay? Just to reduce notation a little bit, one has this cosine of delta here now, this quantity being delta. The last thing that people usually do is that for this situation, one can replace E1 and E2, these are the amplitudes of the waves, by their intensities. And the intensity of beam 1 is E1 squared here with those factors, and E2 is E2 squared. So I can use this one to solve for E1, Just take the 2 on the other side and divide by epsilon c and then square root. And likewise from this one, that amplitude 2 is related to the 2 times the irradiance epsilon times c here. And then plug these in up above to get everything in terms of intensities. And that's what I've done here. If you look at that, you'll have an epsilon c here and an epsilon c square rooted, epsilon c square rooted, so these will cancel. I get a square root of 2, square root of 2, so I get a square root of 2, and I'm left with square root of I, square root of I. And so you get these combined irradiances, or time average valued intensities, of the recombined beam, of the combination of beam 1 and beam 2, as given related to the intensities of the beams separately in this fashion, where delta is really just the phase difference between them, is this factor here. It's related to the distances. Well, to be honest, I don't use this formula much. Usually when I'm looking at situations like this, I generally just rederive, go through these things for the particular situation again, and so I don't. But I know lots of people do. They are always dealing with recombining 2 beams, and they use this expression, or getting 2 beam interference. If we take a look at it, some pretty obvious things. If delta, if it happens that this, when you compute, we know all of these factors, assuming we know all of them, then whenever it's equal to an integer multiple of an even multiple of pi, and so if n is 0 plus or minus 2 plus or minus 4, then the cosine of delta will be 1. And then sometimes people write this as 2m times pi, where m is an integer, 0 plus or minus 1 plus or minus 2. It's just equal to 2m. So you see both ways to write it. One, you have to spell out what n is, and here it's understood that m is an integer. Could be positive, negative, or 0. And in that situation, well, the cosine of delta is 1. And you get the absolute magnitude, the largest intensity you could possibly get is this form here. This is one. Alternatively, you could look at the case where n is an odd, either positive or negative integer. And then again, you might write that n as 2m plus 1, or m, it could be any integer, and that'll make this odd. But whenever delta is an odd multiple of the pi, you get the cosine of delta being a negative 1. That's at 180 degrees basically. And so this factor here becomes negative 1, and you get the smallest value, since it's going to range over all the cosine is only between minus 1 and 1. So when it's at 1, you get the maximum, and when you get the when it's at minus 1, cosine is minus 1, you get the minimum. So you get the maximum and the minimum. If you were to plot these versus delta, you get a function that looks something like this. It's a cosine function that's been shifted up a little bit, and the maximum value is this top line. The minimum value is this minimum line which we've calculated up here. And the intensity is brighter where this is the highest, where the intensity is the highest. And it's dimmer where it's the minimum. It's not 0 necessarily. There's only one particular situation where it's 0. But it's certainly bright and dim, bright and dim. And because of that, sometimes it's, if this is very, if the peak and the trough of this are very close together, sometimes there's not enough intensity for the eye to even distinguish. And with instruments, it's a little easier, a little better. But people define a term called the visibility. The visibility, in this case, of the bright and the dim portions. You actually see it visibly. The light gets dimmer at particular deltas. And the visibility is defined Imax minus Imin over their sum. And you can just plug in the value for Imax and Imin here. And get those once you have the intensities of the incident beam. So everything is based on the incident beam intensities, and then this phase difference delta. Well, the most usual case that people look at is the case where the intensities are equal. Okay? So it's which means that the amplitudes of the two waves were equal. So E1 and E2 had the same amplitude. And in this case, I'll just use I0 for the intensity. So the combined beams now that both had the same amplitude, had the same intensity, I0, plus 2 square root of I0, square root of I0. So I just substitute in the general expression, I0 for each one of these, and have the cosine delta. And combining these, I get 2 I0. I have this 2 out front in our formula, and then this just becomes I0. So I can factor out the 2 I0, 1 plus delta here. And then again, I never remember these half-angle formulas, so just use the half-angle formula. And the way I always remember it, if I want cosine delta here, that's the cosine of delta plus delta over 2 plus delta over 2 is obviously delta. And then this is one trig formula to remember, is the cosine of the sum is cosine of the first term times the cosine of the first term, which is cosine squared, and this one's minus sine squared for the subtraction portion. And then I also know that sine squared plus cosine squared is 1, and so sine squared is 1 minus cosine squared. Plugging all that in, and then taking, I get minus 1 plus 2, and then taking this over the other side. I see that this 1 plus cosine delta, this term here, is just 2 cosine squared delta over 2. So plugging that in for 1 plus cosine delta, one arrives at still a fairly general formula, but two beams with the same intensity, same magnitude electric field. The intensity is I0, and that could be the intensity of either one of the beams, times this cosine squared of delta over 2. And then delta is, as usual, our alpha 2 minus alpha 1. Well, if you also look at these, the minimum value of this, well, cosine, the squared, the largest value cosine squared can be is 1, and the smallest value it can be is 0. I could have the argument such that it's a pi over 2 or a multiple inside here. And so it goes from a minimum of 0 to a maximum of 4 I0. And if you look at that, you get the visibility of this case is maximum visibility. This ratio between the brightest portion and the dimmest portion. In general, the visibility is a number between a fraction between 0 and 1. So in this case, we get the following, that everything gets shifted down, again, plotting the intensity versus delta. One gets this curve here for the intensity, and it goes all the way down. At this point, it is physically 0, so there's no light at all, and very, very minimal light on either side of it. So basically, you have a bright portion, a black portion, no light, a bright portion, and so on, alternating.